Good afternoon, everybody, and welcome to another installation of our quantitative webinar series by the Center of Excellence in Human Development. This is the second webinar in our series out of 6 webinars. And today we're going to be dealing with the topic of regression analysis. Well, I'm your host, Lukang Nyati, and our speaker for today is Dr. Jitin Sam Varghese. And just a little bit of background on Dr. Varghese. He is currently a postdoctoral fellow at Emory Global Diabetes Research Center in Atlanta, USA. He's trained as an engineer and chronic disease epidemiologist. He studies continuous glucose monitoring, etiology of type 2 diabetes from electronic health records, and social determinants of cardiovascular disease among South Asians. He has substantial experience in data management, workflows, statistical inference, longitudinal data analysis, and machine learning in health. As part of his PhD in nutrition and health sciences at Emory University, he studied how wealth over the life course was associated with cognition, health, and well-being in low and middle income country birth cohorts, including the birth to 20 plus cohort, which is here in South Africa at the Developmental Pathways for Health Research Unit. Many of us are familiar with the birth to 20 cohort. Prior to his PhD, he coordinated field studies and developed data products to study the nutritional status of women of reproductive age and children under the age of 5 years in India.
Good afternoon, everyone. It's a great pleasure for me to talk to you all today. I'm very excited about today's topic, and I thank my friend and collaborator, Dr. Lukang Nyati, and the Human Development COE team for organizing this session. So the topic for today's talk is a practical guide to regression, and we would be focusing on regression analysis and addressing biases at the analysis stage. So we will briefly review the objectives of epidemiologic research, review last month's presentation, and then spend most of this hour discussing the concept of linear regression. And we will conclude with a brief summary of quantitative biases in epidemiology. So I encourage you to post questions related to what we have discussed real time, and we can discuss these as we go along. And if at any time you cannot see my slides, or if you feel that I'm going too fast, or if you have any questions at all, just feel free to drop it in the Q&A box. And I would be happy to answer them. If there's any additional information you require, I'd be happy to provide those as well. So the first section is on epidemiologic research objectives. And the first objective is basically to get a valid and precise measure of occurrence of disease or distribution of disease. And these measures of occurrence or distribution consists of things which all of you may be familiar with, measures like prevalence and incidence. Now, by valid, we mean the absence of systematic error. And this is ideally minimized by planning at the design and analysis stages of the study. By precise, we mean the reduction of random error. Now, this may never be fully eliminated in epidemiological studies. And the second objective is to estimate the effect of an exposure on the occurrence of disease. Now, that would mean that we understand the concept of causality. That is, to identify certain generalizable principles within a population that may be amenable to being transported to another population. So you might be familiar with the Bradford-Hill criteria for causality. Now, when we think of the population and the sample, many of you who may have taken introductory statistics class have always dealt with these concepts. But when we look at epidemiological concepts, we need to think of what is a source population. So a source population is a group of people from whom we will sample for our study. And we need to always understand whether we have defined our source population clearly enough. So we can define a source population, let's say, as all children aged 0 to 5 years, or all adults between 18 to 49 years. The second set of assumptions have to do with our study population. So let's say we sample a group of people from our source population. We need to think about, have we sampled them representatively? Do we need to oversample some groups if we want to assess potential disparities, and etc. Now, the final set of assumptions have to do with our analytic sample. So this is a data set we finally analyze after removing those who did not provide complete data or may accidentally be included in our study. So let's say we conduct an analysis using our analytic sample and we get some results. But we need to use our results. So we need to define something called a target population. So the target population may be the same as your source population, or it may be different. Now, we need to make assumptions about how similar these are, and there may be differences in some characteristics. For example, the target population may be wealthier or it may be poorer. It may consist of more men or more women, etc. So we need to find out how different the target population is from a source population. Now, this may be a little vague to some of you, but then once we look at an example, it will become clearer. So let's say we want to apply some policy findings to children under 5 years from a metro in South Africa, let's say Cape Town. And say our source population are children under 5 years from urban Johannesburg, because that's the only place where we can conduct this study. So let's say we conduct an observational study to assess the role of maternal BMI at conception on child height at age 5 years. So I define my study population as pregnant women who are randomly sampled from our source population. And these are the people who would be eligible in our study population. Now, not everyone who is eligible in our study population will be part of our analytic sample. So for example, there may be people who have missing consent or missing data on exposure, missing data on outcome, missing data on covariates, etc. So let's say we figure out some way to statistically deal with this under some techniques. But for now, let's exclude everybody who has not provided complete data. And we hope to conduct an observational cohort study. Let's think of some research questions. So first, what is a statistical quantity that estimates the association between maternal BMI at conception and height for age z-score at age 5? And the answer, most of us know, is called the correlation coefficient. Now, we know that maternal schooling is a confounder of the maternal BMI and height for age z-score association. I would be providing the technical definition of a confounder later, but for now, most of us know that maternal schooling predicts maternal BMI and maternal schooling also predicts height for age z-score. So what is a statistical quantity that estimates the association between maternal BMI at conception and height for age z-score at age 5 after adjusting for maternal schooling? And the answer is a regression coefficient. So in the next few slides, I'll show how these concepts of correlation and linear regression are interrelated and why we use regressions in the first place. So let's look at an expected association and say we define 3 associations. So this picture here on your left is a causal framework of how different variables are related to each other. So let's say the 3 associations are: for a 1-year increase in maternal schooling, maternal BMI at conception increases by 0.3 kilogram per meter square. This is all hypothetical. Then for 1-year increase in maternal schooling, child's height for age z-score increases by 0.1 units. And for a 1 kilogram per meter square change in maternal BMI at conception, child height for age z-score increases by 0.2 units. Let's look at some patterns in real-world data. This plot has 3 pieces of information. The first piece of information is how the 3 variables are distributed. And those are here. And we see that all 3 variables are somewhat normally distributed. The second piece of information how the 3 variables are bivariate distributed as per a scatter plot. Those are the ones here. So for example, this is a scatter plot between education and BMI for the mothers. And the third piece of information are the bivariate strength of association between the 3 variables. So I restate the correlations here. The correlation between maternal education and maternal BMI is 0.432. The correlation between maternal education and height for age z-scores is 0.705. And the correlation between maternal BMI and the child's height for age z-score at 5 years is 0.805. However, as many of you may have noticed, these correlations are different from these values. And these are the expected regression coefficients. And this is because of two reasons. First, correlation is a strength of association when both variables are standardized to have a standard deviation of 1. Second, the regression coefficient and correlation are related to each other as per this equation, such that this expected value of your regression coefficient is approximately equal to your correlation times the ratio of your dependent variable in the regression divided by your standard deviation of your independent variable in the regression. So when you think about your high school math, we write y equal to mx plus c as the line which explains the relationship between one variable and another variable. Here, if we draw that line, for 1 unit change in x, we see that y changes by m units. And when x is 0, which is where it intersects with the y-axis, the value of y would be c. And that is our intercept. However, real-world associations are not so simple, right? We have a lot of noise around this line. So let's say we have a point x1, y1. If we know x1, then the equation, if we just plug in x1 into the equation y equal to mx plus c, we can get an approximation of what y is. And that y, let's say that is that blue point, we get it as mx1 plus c. And that is this point on the line here. But we know that is not the same as y1. So each point cannot be predicted if we know its x values alone. The part that cannot be predicted is known as a residual. And let's say that is E1 for this point. Now, so for a particular observation, we can define it as y1 equal to mx1 plus c plus this residual, which is called E1. So y1 equal to mx1 plus c plus E1. We also assume that the residuals are having a residual variance, some quantity, and a mean of 0. So when we borrow from our previous discussion about slopes, intercepts, and residuals, linear regression tries to estimate these. And the process of estimating these quantities for linear regression is known as ordinary least squares. Any statistical technique will have to fulfill certain assumptions. And in the case of linear regression, these are x, which is your independent variable, and y, which is your dependent variable, are linearly dependent. The residuals E, which we spoke about, they're normally distributed. Residuals have the same variance at all values of x, with this property is known as homoscedasticity. It's a mouthful, but it's a very fancy way of saying that they have the same variance. Residuals are independent of each other. That is, there is no autocorrelation, another statistical term. And finally, there is no or little association or no multicollinearity between the independent variables, which are your x variables. Now, we will take a look at each of these assumptions separately and how to handle the violations in these assumptions. Okay, let's look at the first assumption. So dependence implies that there is some non-random association between your independent variable and your dependent variable. So for example, if x increases, y should increase linearly. Now, we can examine if the variables are linearly dependent by plotting a scatter plot. And if both x and y are continuous, in which in our case they are. Now, x can be categorical, and in that case, this assumption does not really matter. But what happens when they're not linearly dependent? Let's say here we see like some sort of like a weird shape, which is not a straight line, that it's flat and then it goes up and then it like decreases in slope. So we need to use some methods that account for this nonlinearity. There are so many methods out there. For example, one of the easiest is to add quadratic terms of x. And if you can make it more and more complex, the more you learn about statistics. Now, so here I show the output from Stata on what happens when I run the linear regression using the command reg or reg. We see that we have an estimate. Here I'm calling them averages. We have a standard error of these averages. we have a t statistic, which is basically your average divided by a standard error. So which is, in this for BMI, it is 0.196 divided by 0.004. And you get the t statistic, which is equal to 39.58. And we have a p-value, which is a probability that your t statistic exceeds a particular cutoff. In this case, we're putting the cutoff at like 1.96 under assumption that this is null. And finally, we have the 95% confidence interval for this particular estimate, which is basically 0.196 minus 1.96 times 0.18 and 0.196 plus 1.96 times 0.04 times 1.96 plus 1.96 times the standard error, which is like 0.004. Now, this confidence interval has like some useful properties, and this is what typically we use for hypothesis testing. Now, I want to point out that we expect an association between BMI and height for age of 0.2, and we see that it is pretty close. It is like 0.196, and we expect an association of 0.1 here, and we see that it's like about 0.097. Here, height for age is a dependent variable, BMI and EDU are your independent variables, and this represents your y-intercept. Now, the first thing which you need to look at is whether the formula which you use is correct, and in this case, it is. Height for age is your dependent variable, BMI and education are your independent variables. Now, when we get the output of linear regression, we get some additional things apart from this table, and those are very important to look at. So, for example, here we have something called the F statistic. That is basically F2997 equal to 2049.92. I will be describing what this is in one of the later slides. And we see that the probability that it is great, the F statistic is greater than the cutoff is 0.000. This is a p-value. And I will be explaining this in the next slides. So here we see something called model, residual, and SS. Model and SS, this is a model sum of squares. And residual and SS, this is the residual sum of squares. Here, we also get a quantity, which is the total variance, which is the sum of these two, which is 389.95 plus 94, which is 484, divided by n minus 1. And in our case, let's say n is 1000, and n minus 1 is 999. And we get this quantity, which is in fact equivalent to the total variance of your height for age. So it is 0.485. Okay. Let's look at some more outputs from linear regression. Sorry, I skipped the slide accidentally. Now, so in the first case, we spoke about the variance being 0.485 that we see here. The variance unexplained, that is the residual variance, is a mean squared error, which is the same as your residual standard error times residual standard error squared. So that you get is basically what you get is if you take the residual sum of squares and you divide it by 999. So it's 94.82 divided by 999. The variance explained by the model is 0.485 minus 0.095. So this minus this. Now, the number of regression parameters is 3. So we have 1, 2, 3. And you have a number of observations is 1000. That is what is given here. The mean of squares for the residual would be this parameter, which is basically the variance unexplained, times n minus 1 divided by n minus p. This is 0.095 times this quantity. You can also get it by simply dividing 94.82 divided by 997, and that's what we get here, 0.095. And finally, the mean of squares for the model is this quantity, the variance explained by the model, times n minus 1, which is your 999, divided by your p minus 1, which is 2. Or simply what you can do is you can just take this and divide it by this in order to get this. So 389.95 divided by 2 equal to 194.975. Now, these are the same 7 parameters which I spoke about previously. And when we often hear of a concept called R square, which is a share of explained variance in the outcome, which basically is the variance explained by the model. In this case, it is 0.390 divided by your total variance, 0.485. Then there is something called the root mean squared error, which is the square root of your variance unexplained. The F statistic, which I mentioned about the overall model fit, tests an alternate hypothesis or tests a null hypothesis that all regression parameters are 0, or equivalently, at least an alternate hypothesis if at least one regression parameter is non-zero. And that can be derived by G by F. And then next you have the adjusted R-square, which is a very complex formula. But what adjusted R-square does beyond the simple R-square is it accounts for the number of parameters which you fit into the model. The adjusted R-square and your regular R-square are very similar if your sample size is large. Okay. So an anonymous attendee asks, what is the interpretation of underscore constant? So this is a y-intercept. So as we explained before, like when both of these parameters are 0, the y value will take a particular value. In this case, it does not have a real meaning. So when you think about it, BMI can never be 0. Even though education can be 0, BMI can never be 0. But hypothetically, let's find a person who is like having BMI of 0. What would be the value of height for age? And that is what underscore const says, which is basically your y-intercept. Okay. Now, the second assumption which we need to consider is the normality of residuals. So what we need to do in this case is that we need the residuals to be normally distributed for the linear regression, especially in small samples. Some people mistaken this as the dependent variable has to be normally distributed, but often like the issue is that the residuals are not normally distributed, and that's what we need to plot and see. So we can get the residuals from Stata from the predict residuals command, and we can plot the residuals after that using the histogram command. But what happens if it is not normally distributed, like the top graph here? We can often like do a log transformation of the outcome. And once again, clarifying the outcome and not the residual in this case, so that we end up with normally distributed residuals. So we always log transform the outcome and we get normally distributed residuals. And we always need to assess the normality of the residuals, not the y. And more often than not, the normality of the y would imply normality of residuals. Next, the third assumption is that the residuals have the same variance across X. So I spoke about this very complicated term called homoscedasticity, which is basically the assumption of equal variance across observations. So here, what we need to do is we need to plot the residuals of the linear regression on the y-axis and the independent variable maternal BMI at conception on the x-axis. And we need to see whether the spread is like similar across different values of maternal BMI. Now, what happens when this is violated? So we can transform the dependent variable to get a homoscedastic variance. So here as well, log transformation can help if the outcome variable is very right skewed and is always a positive number. And there are other transformations also that we can use. For example, we can take the square root of the outcome variable that will give us a more homoscedastic and less skewed distribution. Now, this also may be a new term for at least some of you. So whenever I heard this, I found it scary because I couldn't understand how a variable could be correlated with itself, since we usually do correlations between two variables, right? However, what this means is that the previous value, which could be the immediately prior value or a value which may be much before this. Okay, so Rachna asks, what pattern should we look for when interpreting the homoscedasticity plot? So when typically what we need to look for is that there should be no pattern at all, and it should be similar across the different values. So the width should be similar over the range of your independent variable. Okay. Now, as I was saying before, like when you run correlations, you try and run a correlation between two different variables. But what this means, what autocorrelation means is that a particular value may be dependent on a variable which is like much before. So it can be like the immediately prior value, or it can be a value which was collected maybe a couple of weeks ago or from a different person living in the same household. So the technical definition is that there's a correlation between residuals or observations that are clustered in time and space. Sorry. And these are often visible as patterns after nonlinearity has been accounted for. So this is basically what it should look like when there is no autocorrelation. It is like it's totally random. Even though it does look like there is some pattern, but in fact there is none. Now, autocorrelation happens because observations are clustered in time and space. Time or space, rather. And this underlying process can be thought of as, let's say we typically sample in a survey individuals from a particular household, and then we sample households from a particular village or from a ward. So one individual who resides in a household has a high chance of being sampled if their co-resident is also sampled. This is known as spatial clustering, and we need to account for this. The problem is that linear regression, it treats each individual as being sampled from the same population with probability of selecting one individual, not affecting the probability of another person being selected. You can think of it as like you being selected should not interfere with the probability of somebody else in your community being selected. But often that is not the case, simply for like financial reasons. Surveys tend to maximize the efficiency of sampling, so they tend to sample from clusters. So Dr. Will Johnson would be covering some methods related to this topic on September 5th. And he would specifically looking at mixed models and certain growth models which account for autocorrelation in time. Now, there is another term which may be new to some of you. The first time I heard it, I did not understand what this was. Multicollinearity means that independent variables can predict each other. So what this leads to is that we cannot clearly say if the association is due to one variable or the other variable if both variables are correlated with each other. So typically, correlations have to be greater than 0.7 for this to be a problem. And we can check this by using a quantity known as variance inflation factors. Now, these quantities tell us to what extent variables predict each other. And a VIF greater than 5 or greater than 10 are considered big. So in our case, these are not that big. And how do we account for this? We need to select variables that aren't correlated with each other based on expert opinion. Dr. Alice Kowalski would be covering one of the more advanced methods to deal with collinear data on September 29th. Now, these are some of the more fascinating concepts in linear regression. I personally find them very satisfying to understand. So for example, if we plot X and Y, we may see that a point does not align with the other X and Y data. For example, here, all the points are here, but there is this one person who is like somewhere here. And in this case, all the points are here, and there was one person who's somewhere here. If a point consists of large X values, that point is said to have a high leverage to influence the regression coefficient. Now, if we have large or small Y values related to the X values, it may indicate that the data is coming from a different population, and this presents a bigger problem. Because in this case, you can actually draw a straight line and this value will still fall within this line. But here, this point does not fall within the regression line. And what it might do is that instead of the line going like this, which represents a true association, the line might in fact become something like this in order to capture. So the line might go like this in order to capture this particular point's weight also. Because like I said before, linear regression treats all observations as coming from the same population. So this is a bigger problem for our estimate, because instead of saying the slope was like this, now we are saying the slope is like this. So let's do a quick recap. Let's conceptualize the linear regression as an estimation of the regression line, which consists of the slope m and the intercept y, and the residual variance under a particular assumption or particular set of assumptions. So the other thing being, if we have issues with the slope estimation, you may not have issues with variance estimation and vice versa. This depends on the particular assumption being violated. So example, if you have multicollinearity, which is when your independent variables can predict each other, your variance would be correctly estimated, but your slope will not be for the correlated variables, assuming everything else holds. So let's use linear regression to estimate slopes and ANOVA to estimate the means of a continuous variable within the levels of independent categorical variables. So if independent variable is categorical, your slope in your linear regression would give you the mean differences between the levels of the categorical variables. So linear regression, ANOVA, basically the same thing. They both try to estimate the mean difference or the slope, except in linear regression, you can deal with both continuous variables as well as categorical variables as independent variables. The next one. You might have come across other regression models like logistic regression or Poisson regression. These are all similar, but linear regression primarily deals with the normal distribution, while the other regressions deal with other distributions. For example, logistic regression deals with the binomial distribution. Poisson regression deals with the Poisson distribution. And this is for binary outcomes. This is for count outcomes. And if you see, all these four regressions have the same or a similar independent variable format. They're all linear combinations of independent variables. But they're different in how they treat the outcome variable. The next thing which we need to think about is what's weighted least squares. So ordinary least squares have certain assumptions that we discussed. And one key idea is that all observations are treated equally. Now, what happens when some of these assumptions are violated, that there is no homoscedasticity, or when you have outliers or high leverage points? We can incorporate weights to change the relative contributions of different observations of regression. A big challenge is deciding how to allocate weights. Now, when we conduct a multi-stage sample survey, we select a province, we select a municipality, we select ward, select household, select people. So we need to account for the different probabilities of selection of people into the study by strata and by clusters. We can use a weighted least squares approach for coefficient estimation. However, we need to account for this non-independence, alternatively the clustering within different stages of the survey. And that would give us better values of the standard errors and residual variance. Now, there are a lot of things which we haven't covered so far, and it might be good to just maybe Google these things up and learn it yourself. And now, I would want to talk a bit about something called quantitative bias analysis. This is a topic which is often under-discussed in most introductory courses on statistics and epidemiology, and for good reason, but it is important to know for all of us because we work in the sector where we have a lot of biases because we're dealing with people. Now, bias is when your regression coefficient is different from your true association, or your observed value is different from your truth. And all biases are missing data issues. They can be missing data in observations, which is selection bias. They can be missing gold standard measurements, which is information bias. Or they can be missing variables that may explain the exposure outcome association, which is confounding. So let's say we don't collect the data of maternal education, and we try to estimate the association between maternal BMI and height for age at age 5. We are not estimating the true association between the independent variable and the dependent variable, and that is confounding. So let's look at what selection bias is. So selection bias happens when we try and estimate something in our study population, but it differs from what is a true association in our population. And this can be because of many reasons, but commonly this is because of factors that are related to both the exposure and the outcome and are involved in selecting the sample for our analysis. So for example, there may be lower participation among those who are poorer or who are minority communities and who may be susceptible to both lower BMI and lower height for age. In a randomized control trial, those who are given the drug may drop out at different rates from those who are given the placebo due to side effects, but the reason for dropout is not reported. And finally, in the cohort studies, participants who are rich or poor at baseline may migrate from the study site or may refuse to provide the data. This is how selection bias happens. Now, the first thing you need to do when you're dealing with selection bias is to compare your participants in your analytic sample versus those who you're excluding and try to see if there are any differences. For example, if your analytic sample may have more people who are from wealthy backgrounds, who are undernourished at baseline, we need to report that. The next thing is you need to figure out a way to incorporate these differences in your analysis, and this requires more complex methods. Confounding is something which all of us are familiar with and we use almost daily. But I want to discuss this a bit further. So confounder is a third variable, which is not on the causal pathway between the exposure and the outcome. And is associated with both the exposure and the outcome. And therefore, it may explain the crude association of the exposure and the outcome. So which means that confounder cannot be a variable, which is a mediator. So between maternal BMI, gestation, and height for age 5, it cannot be something like birth weight. Now, what are some potential confounders in our case? In our case, some confounders can be how wealthy the parents are or maternal smoking. And typically, what you need to do when you think of a confounder is to do a proper literature review and identify all the variables that can predict your exposure and the outcome. And we need to adjust for those variables in your regression model. And linear regressions are good if your assumptions are met. And yeah, if your assumptions are met and your confounders are included as adjusted variables. Now, finally, the last error which I want to talk about is information bias. And this has got to do with measurement error or misclassification of not only your exposure, your outcome, but also your covariance. So on the figure on the right, we have an association between a gold standard exposure and a gold standard outcome. Sorry, I mean like figure on your left. So, but what we end up measuring is different from the gold standard outcome or the exposure because of how sensitive our instrument is, or simply because it cannot be measured well. An example is, let's say, diet. We all know that diet is very difficult to measure. And so what we end up measuring may be very different from the true association. So some ways for information bias is that we have data in our study on last menstrual period that is self-reported. The length or height of the child is measured using a wooden scale and not a stadiometer. This is something which I dealt with in one of the studies which I was a part of. And the reviewers were like very strict about this. Or the measurement may have been due to unstandardized protocols. Finally, a maternal BMI may be self-reported for some individuals, while it may be from the medical records for others. So we end up with incorrect estimates of this association. This is what we actually want to estimate. This is what we end up estimating. Okay, addressing information bias. The first thing we need to understand is why we're mismeasuring items. And next, we also need to talk about interpreting the results in a very conservative manner. So we need to talk about this mismeasurement in our results and discussion sections. And once you do these 2 steps, you can incorporate this into our statistical models. This step is pretty complex and requires some advanced statistical models. And so finally, this is our end of our presentation. So I'm providing some useful textbooks which may be helpful. Please feel free to reach out in case you need any additional clarifications. And I'm happy to take more questions at this stage.